Hello fellow problem solvers. So today we're going to be doing problem number 2 from 2022 IMO. This is a beautiful, I like non-standard functional problems. Like those are some of my favorites when they're non-standard, not just plug this in, plug that in. Like that's nice, that's technique. It's good to test that out. Sometimes that can be cool, but this is one of my favorite types. So the problem itself is nice. Now I suggest you try this out for a minimum of 20. Ideally, actually, I'd say ideally an hour to 90 minutes, not more than 4.5. You wouldn't have that much time at the IMO anyway. And without further ado, let us begin. So let's look at this. Such a unique problem statement, right? For every x that's in R plus, so we're dealing with R plus, there is exactly one R. There's exactly one y in R plus, such that this is true. And this functions from the positive reals to the positive reals. So how do we even begin this? I invite you really pause for 5 minutes, think about this statement and think about what can you do with that? Or maybe what is the solution to this? Like, do you see anything? And for me, when I was looking at this, I was like, okay, wait a second. So f of x cannot be a constant because I'll have c times x plus y less than or equal to 2. I can find, like, there's some x for which I won't be able to find, this thing. If x is greater than or equal to 2 times c, then I won't. So anything to do with floors, it might give me two solutions. So that's not it. F of x is equal to x just gives me xy less than or equal to 2. Infinitely many y satisfy this, but this says only one such y. Oh, what about 1 over x? And I see, okay, then if f of x, so if f of x is equal to 1 over x, then this becomes x over y plus y over x, like for every single x and y. And so, but this is greater than or equal to 2 by AMGN. And there's only one solution, and that is x equals y. Okay, so now this is cool. And I invite you, with this, think for 5 minutes, like, what would you do with this? How would you push the problem further? And here are like a couple of different things to note here. So first is, some of these numbers are paired up. Like if for x, it is like y is the unique one, then for y, x is the unique number, right? It can have some other unique number, okay? Now, what is x paired to? And this is where I went wrong, like not thinking about this. And I was going down the wrong path for a long time. And I might pause for 5 minutes, think about what is x paired to? Like in our solution. Well, x is paired to itself. Like every number is paired to itself. I assumed only one was paired to itself. And I was trying going at it, trying to prove that. But no, for every x, there's only one y, and that is itself. I thought it was 1 over x. That's the y that satisfies the relationship, but the answer is no, it's not. So with that in mind, we have a functional equation that works. And write this down if you see it. Note that f of x equals 1 over x works because of this. And now we're going to continue on trying to solve the problem. So what are some ideas that might come up if x isn't tied to x? That means for every other thing that's not y, so for z not equal to y, we must have x f of z plus z f of x to be strictly greater than 2. Okay, now, is there anything we can do maybe with these things? Now, I invite you to pause for 5 minutes, try to push the problem further. Let me clear up the board and write everything down nicely. Now that we've cleared everything up, let's think about this. So, x should be tied to x. We have that. Now, let's think, we can go about it a couple of directions. This is a solution. This function is also what? It's surjective, that's one thing, but it's also injective. And that seems like maybe we could actually prove that if f of a is equal to f of b, then that we have a is equal to b, a problem. So let's assume it's not the case. Let's assume, say, f of a is not equal to f of b and a is greater than b. then there exists a unique y for a such that y f of a plus f of y a is less than or equal to 2. But now what do I have here? Well, this is equal to y f of b plus f of y b, and this is strictly greater than, this is equal to f of y times a, which is strictly greater than y f of b plus f of yb. And now, a is tied to y is connected to b as well. But then for y, both a and b satisfied the condition, so this isn't true. And in fact, this equality wasn't what I needed. I just needed a less than sign, right? Less than or equal to sign. To get like less than or equal to, in fact, to get a contradiction. So now if a is greater than b, if f of a is greater than or equal to f of b, I'll still get this same contradiction. So this implies that f is decreasing, and strictly so, which is what we need to prove. Now, it's important to note this thing might be combined with the solution 1, 2, maybe even 3 points, depending on the grading scheme. And write these things down. As I always say, points, like 1 point can be useful at the last page of the problem if you're low on time. Just write down all the facts or keep track of all the facts you have, especially about geometry's functions where that is not difficult to do. Just keeping track of the facts isn't that difficult. Figuring out what facts are important is difficult, and figuring out what the facts are is also difficult. Now, we have this decreasing. So what happens if x isn't tied to x? If x is tied to some y, that is, and y isn't equal to x. Pause for 5 to 10 minutes and try to push the problem further. Think about this case. What happens here? And the answer is okay. Well, we know that for everything else, if x and y are paired, then everything else is greater than 1. So we have x times f of x. Here, like if I plug in x and x, I'm going to have 2 times this is strictly greater than 2. In other words, x times f of x is greater than 1. And the same thing needs to hold true with y. Y times f of y is also greater than 1. So in other words, both f of x and f of y. F of x is greater than 1 over x, and f of y is greater than 1 over y. We're into positive real numbers, so we can divide these inequalities. And now what do we have? We have f of x times y plus y times f of x. Well, let's see if we can get a contradiction using this. Well, we have that this is greater than y over x plus x over y. Okay. And this is now greater than or equal to 2 by AMGM. A contradiction. 2 is strictly greater than 2. We get a contradiction. So, what does this mean? It means that every x is paired with itself. I haven't seen the marking scheme yet, but I think this should be about 4, maybe even 5 points. Write even the little things down. And now let us continue. Okay, so we've looked at, like this was the main idea here, to look at, okay, what is paired up with what? What? When you're looking at the problem backwards, seeing, okay, this is what my solution probably is. This doesn't always work. Like sometimes you can go down the wrong path if you don't check for all the solutions. But we've done some thinking, like, is the fraction, like is the floor part, doesn't make sense, anything non-continuous, does it really make sense that that could be a solution? Could we easily get 2 or more things that hold true? Like, it doesn't seem simple to also just, like, it seems like it should be continuous in some way, shape, or form. And we don't need to prove continuity right away because, it's the IMO. I'm thinking it's maybe not there yet. Problem number 2. But, let's try with simple ideas before we try to prove something like continuity. Like, this is monotonicity. It's strictly decreasing. That's fine. Now, let us continue with this. I invite you here, actually, with this in mind, pause for 10 minutes and try to push the problem further. I'll write everything we have down in our facts page. And, okay, let's just clear this up. So, we've cleared everything up, and now with our facts page, we have this. F of x is less than or equal to 1 over x for every single x. Now, what happens if f of x is so it's less than or equal to 1 over x. Like, how does this change our thing? It doesn't change it by that much, does it? It's less than or equal to something. I can't go, like, I have 2 less than or equal to f of something, and I can't have, well, this is less than or equal to something else. If I did greater than or equal to something, I maybe could work with this. So my question is, how do I deal with that? But maybe, 2 is, strictly less than f of x times y plus y times f of x for every x not equal to y. Maybe there's a thing we can do here now. Like, we know that every one of these is with themselves. And if we know that every one of them is like connected to themselves, f of x is less than or equal to 1 over x, we've sort of used the condition about uniqueness less than or equal to 2. So it only makes sense now to look at this condition when for all the other ones that are not the same, this holds true. Now we should, somehow using this fact and this fact, like this is everything, the fact that it's decreasing as well. Using these 2 facts, we have our problem. Like, this is sort of what this problem is boiled down to. X is connected to x is this. The f is decreasing portion is for uniqueness. These 2, I believe, would give us the uniqueness, and I'm even not sure if f is decreasing is important, but this is what the problem has boiled down to. So, what do we do here? Like, what if f of x is strictly less than 1 over x? How do I actually, gain some insight from that? Say if I fix some x, actually, this should be x f of y. If I fix some x, what am I going to get in terms of y? Like, what is f of y like? Well, if I fix any x, I get 2 minus f of x times y over x. F of y is strictly greater than this for any y. Like, this is just looking at things in a different way. Now, this must always be true. A question that's maybe this is another direction we could go with this. If we can prove this is always greater than or equal to 1 over y, like if, for example, one sort of direction would be, to go at it from both sides. If f of x is less than 1 over x strictly, maybe there's a y such that this is true. I don't know if this is the case, but you need to come up with some hypotheses, some ideas for what could happen. And let's see if this is a valid route to go down. They're trying intuitive stuff. I'll go down a different route also, where we can think about this in a different way. Like, another way is to say, okay, if f of x is less than this, let's say f of x is equal to 1 over x plus some d. Some d is positive. Let's see what's going to happen to this d. Like, that's a different way of thinking about it, but I'm trying to show to you different approaches to this solution. I think this is pretty linear in this thinking if you're focused on, okay, like this question, okay, wait a second, x is connected to x. Can I prove that? And it turns out you can, and then we're down this rabbit hole. And unless we get to a problem, let's do this rabbit hole. And I like this one because this is now our problem. This and this is really our problem. I might even, combining these 2, might be able to get that f is strictly decreasing. Not super sure about that. But let us continue. So we have, if this is the case, what would need to happen for us to get this sort of thing? Or even equality. I need to have, so x over y would need to be 2 minus f of x times y. I need to have f of x times y, less than or equal to 2, plus x over y to be less than or equal to 2. I'd really need f of x, okay, if I'm just writing things out in terms of f of x, to be less than or equal to 2 minus x over y. this is, I'm going to need to pick a specific y to make sure this is the case. I just need to make sure that that this isn't negative. So if this is positive, then y is greater than or equal to or less than or equal to 2x. I think it's greater than or equal to half of x. So I need to show that, okay, if x is less than 1 over x, can this in fact be the case for some y? For some y that's bigger than this? Like, that is the question. Could this make sense? So if this was equal to, say, some 1 over x plus d, now what would I need? I need to have, have I made any arithmetic error is my only question here so far. I've multiplied everything through. I have done the 2 minus that. On this side, 2i minus x needs to be positive. However, y doesn't seem like I've done anything sinful here. Like, this all seems to be working quite nicely. But let's push it forward, and I invite you, in fact, push it forward for the next 3 minutes. And I'm going to, make this all nice and clean over here. And what I get is, once I write this down, and I want to use this condition fully, so let's say y is x over 2 plus some epsilon, and I get this. Well, now I'm thinking, wait a second, this should be okay if, if d is equal to 0, and it is okay because this is greater than or equal to x times epsilon for some epsilon. And now what does this transform into then? So then this here is equivalent to, once I move x epsilon on this side, this is x over 2 minus epsilon squared needs to be less than or equal to epsilon times d. So now if I just set epsilon to be equal to x over 2, then this thing will be true, and then so will everything else. So then this thing will be true, and this thing will be true, and with that, this thing over here will also be true. And from there, it seems like we're done in a weird way. So this has been x half minus epsilon. What has happened here? This is x minus y squared. We need to double check our work. Okay, so if I move this times x to this side, yes, this is equivalent to, yes, y minus x squared less than or equal to 2y minus x times x plus d. If this is fixed, if I just set y is equal to x even, I get a contradiction, but okay, y is not equal to x, y needs to be different from x. So I just need to set this to be very, very close to, so x and y to be incredibly close to one another. And I'm pretty much then golden. Then I have, so if I was to set x and y, if I was to set instead of this here, if I was just to set x minus y, so x minus y is equal to some t, what does this transform into? This is t squared. T squared needs to be less than or equal to, for me to get my contradiction that I want, this needs to be less than or equal to x plus d times, what is this? 2y minus x. So let's say y is going to be bigger than x, 2y minus x. So 2y minus, so this is d times t plus y. And now I need to make sure that this is true if d is, no matter how small d is. If I set y to be equal to this, then as long as this thing holds true, I am good. My t depends, I don't like that I have way too many dependencies here. Like my t depends on my y. I want to set t incredibly small. Let me divide by t squared to see if that is what I actually want, d is greater than or equal to 1 over t plus y over t squared. Can this be as large as I want it to be? I'm not sure. Do let me know if you can finish this up like this. Maybe I'm not seeing something. So let's go down this route. And what happens when we clear up the board is we have this. So now let's use this for y to just like see what's this is going to be less than or equal to, and that is going to be y over x plus d plus x over y. Okay, y is variable. I want to show that this thing over here is less than or equal to 2 for me to get a contradiction. What is the best y for me to do that? Well, this is a function in y. And if you, like, there's many ways to think about it. I think this is just like algebra at this point. I mean, it is an algebraic problem, but at this point, it's a function in y. There's a couple of ways you can think about this function. Say that it's equal to, like I'm thinking about this, like this is also a quadratic function in y. This is y squared plus x times x plus d over y times x plus d. And its minimum is reached like if y is very big, much bigger than x plus d. This is bigger. If y is much smaller than x, then this becomes big. So it's in that middle where they meet. And the middle here is, I believe, where y is equal to the arithmetic mean of these two. So if I set y to be equal to x plus d over 2, this is my best bet for the minimization. I'm going to get that x plus, okay, let's say d over 2 is equal to e, x plus e over x plus 2e plus x over x plus e. I want to show this is less than or equal to 2. And this is true if and only if x plus 2e times x plus x plus e squared is less than or equal to 2x plus e, x plus 2e. Okay, now this is x plus e squared over here. I have x plus e squared. I'm going to have it, if I had a 1 here, I'm going to have that twice. So it's minus 1 less than or equal to 2 times x plus e squared plus e times x plus e. These cancel out. And this is true if and only if 1 plus x plus e times e is greater than or equal to 0. This is obviously true. So, because x and e are both positive real numbers. And so this thing over here is less than or equal to 2 for y equal to this. And now y equals d over 2 plus x. This is less than or equal to 2. And so we get a contradiction. If d was 0, we would have setting y is equal to d over 2 plus x. We'd have x equals y. So no contradiction there. But because we're saying that x is equal to this for some d that's bigger than 0, we're getting a contradiction. And so the only function that does work is f of x equals to 1 over x exactly. And this finishes up the problem. It is not tremendously super duper difficult for number 2, I'd say. And judging by the results, I think about 300 people got a 7 on this problem, which is a lot. Like around 370 people got a 7 for the first problem. So this is a big number, but it's I like the problem. I like that it's non-standard. Sure, it might be an easier algebra, but that's why this year's IMO had a bigger boundary for bronze. This finishes up our nice functional equation problem out. If you do know of a different solution and you've thought about this differently, please do let me know in the comments below. And as always, thanks for problem solving.